Hi, welcome along to a video podcast on orbit. We're looking at the International Space Station here, not a simulation or anything like that, it's an actual picture. So we've got a huge object there, it's undoubtedly got a lot of weight, a lot of force pulling it down. Got to be accelerating downwards therefore. So how on earth does it stay there? And I guess that's what we're going to try and work out in this video. Got a little simulation here for you. So we've got two objects and it's just going to model gravity, and I can edit the velocity of this object here, but we're just going to do the obvious and start off with it not having any initial velocity. Yeah, pretty obvious, just like I said before. That object wants to accelerate straight towards the more massive object there. So we can imagine that the yellow thing is, say, the sun, and the pink spot is the Earth. As soon as we turn on the simulation, gravity takes over and it accelerates it. So let's just try giving it a little bit of velocity. Okay, all right. So actually, we've already started to create something a bit more usable. It's still accelerating down, isn't it? Okay, let's just try a touch slower. But it's got a little bit of sideways velocity. Okay, let's try again, a bit more sideways velocity. Oh, right. Okay, we're getting there. I'm just going to do a bit more. Let's try that factory default. Still not quite a circle, is it? So let's just go very slightly faster. Okay, not a bad orbit there. So what's happening? Well, that pink dot is still always accelerating towards the yellow dot because it's in a gravitational field. It's always accelerating in that direction. However, it's also now got a sideways velocity. And if we remember what an object's doing when it's in circular motion, we'll remember that an object in circular motion is always accelerating towards the center of the circle. So what we've done here is we've kind of rigged it. So we've used that acceleration to be the centripetal acceleration of the satellite. So let's take a freeze frame of the orbit. It's not quite perfectly circular, and we're only really supposed to be doing circular orbits, but I'm sure you'll agree it's still a better circle than if I'd drawn it by hand. So I'm just going to try and flesh out what I was saying before. So what we know is that this pink object is accelerating in that direction. How much acceleration has it got? Well, the field strength at that point will be given by the equation Gm over r squared. So the field strength gives us the acceleration at that point. We've seen there's nothing we can do about that acceleration. It is accelerating towards the planet. However, we've given our object an amount of velocity v. We've already used, I'm just going to change pen color here, the idea that this distance is r. The object's moving in a circle radius r. So we know that the acceleration required towards the center of the circle for this to be in circular motion is v squared over r. So if I was teaching this lesson live, I'd have teased you a bit and I said, is this object in orbit in equilibrium? And it's not in equilibrium. Its velocity is continually changing. It's always accelerating towards the planet, so it's not in equilibrium. So an orbit is the happy kind of marriage of these two things. It's the marriage of that and the marriage of that. We're saying the acceleration it needs anyway to go in a circle, v squared over r, is exactly equal to the acceleration it will get due to its position in a gravitational field. Now, I'm sure you can see that we could simplify that by removing one of the r's, but those two equations are both on the data sheet. That's the centripetal equation. That's the equation for g, acceleration due to gravity. And by putting those two things together, that allows us to define an orbit. Just going to put some numbers in here and then give you the job of seeing if you can work out how fast the satellite must be traveling to go into a circular orbit around the Earth of a certain radius. So I've just got the data sheet in front of me, and it tells me that the mass of the Earth is 5.97 times 10 to the 24 kg, and that's in the bottom left-hand corner of the data sheet. We already know that g is 6.67 times 10 to the minus 11. And I'm just going to give you the radius of the orbit. We'll give it a nice round number of 7,000 kilometers. One of the things that's going to confuse people, and it really shouldn't if you think about it, is that, okay, there's our orbit, there's our planet. If I say the radius of the orbit, I mean how far is the satellite from the center of the planet, and then that's the r in our equation, v squared over r equals gm over r squared, and then mathematically that's straightforward. Sometimes a question will say the satellite has a height of 200 kilometers above the surface of the Earth. Well, we can't use that 200 kilometers in this equation because that's not the radius, is it? It's not the distance from the center, it's the distance to the surface. And we would then have to add the radius of the Earth. And if you stop and just pause and think about that, I'm sure that makes sense. But you will see students, like in this question, and they'll take the 7,000 kilometers and they'll add the radius of the Earth. You don't need to add the radius of the Earth to the 7,000 kilometers. It is the distance to the center. So what I would like you to do is to plug in the numbers. We now know, just use the highlighter. We now know G, don't we? We know M and we know R. So what I'd like you to do is find the velocity of the satellite. So let's just quickly go through this. We've got v squared over r equals gm over r squared. We can quickly cancel that r with that, and there gives us v squared equals gm over r, which means that v is the square root of gm over r. So what's going into your calculator, I'm not sure I've got space to write it all, is 6.67 times 10 to the minus 11 times 5. Yeah, you can see why I usually write on a bit of paper. I might get there with this eventually, but I'm not there yet. 5.97 times 10 to the 24, and that's all over 7,000. And you did remember to convert it to meters, didn't you? Drum roll, please. And that gives us that the velocity of the satellite is 7542.25 meters per second. I think we can round that back to a much more reasonable 7,540 meters per second. That is really fast. Supersonic planes going about 700 meters per second. So we're talking about 20 times the speed of sound. That's why going into orbit is so hard. You have to go really, really fast. Give you some examples to try now on a worksheet.